So in this last hour, we will first very briefly talk about one last aspect related to circular Poiseuille flow or pipe flow, and then we will go to the vorticity transport equation. So my last comment would be just a comparison between a plain Poiseuille flow, where we just looked at, so plain Poiseuille flow, and here we have the circular Poiseuille circular Poiseuille flow, where the idea was that it was actually kind of like this. And maybe here actually I can be a bit more verbose in kind of the way like this. So this is the plain Poiseuille flow with a certain width d and a certain height, and this here would be the circular Poiseuille flow, where I have the velocity profile kind of like this. Now, the idea is that in both cases, we actually have a parabolic velocity profile. So if we just look at this profile, this here would be a parabolic profile where we have u center line in the middle, and we can have this bulk velocity ub. And the relation, as we have just calculated before in plain Poiseuille flow, was ub is 2/3 of UCL. So this was the relation that we just did before, and I did the integral wrong, as you have noticed. So this is for plain Poiseuille flow, but we can do the same game also here in circular Poiseuille flow, so in pipe flow. So imagine that I'm doing a cut here through the center, and then I will also have this parabola, which kind of looks like this. Also in pipe flow, I can define a bulk velocity, which then would be kind of, this is the cross section, and then it would be the same. It's a bit difficult to draw, but kind of something like this. It's kind of a ring, kind of a cut from a pipe that has everywhere the same size UB. Again, also here we have in the center UCL. Now the question is what is the relation in pipe flow between UB and CL? And also this is something we'll calculate later on, but actually just for now, I just wanted to feel your feeling here. And I'm having prepared a poll here. So the question is, for circular Poiseuille flow, how does the center line velocity compare to the channel flow? If you have fixed mass flow, if the Q is constant. So the question essentially is this UCL? Oops. So this UB, how does this relate to UCL in pipe flow? So either is it 1.5 or 2/3 if you write it in this way, as in channel flow, or is the factor here maybe a factor of 2 or 1/2, or is it 4/3? So what is the relation between UCL and UB in circular Poiseuille flow? What do you think? Is it 1.5? Is it 2? Or is it 4/3, which is kind of 1.3? Then in pipes it was 1.5. What is it? In channels it's 1.5. What is it for pipes? And of course you can do an integral and do it properly, but I just asked you to kind of think how this should be. And let's think together very briefly. So I see here the results, and it turns out that most of you say it's, so the results say that UCL is 4/3 of UB, and that would be a bit lower than in channels. So let's think a little bit. You have a pipe which is round, and the highest velocities obviously are in the center. Now, in order to balance or to calculate the average over a circular area, it of course means that the region in the center is proportionally less present in this integral. So the area of the center region is proportionally less than in a planar geometry because of the round geometry. So that means in the average, the center where the highest velocities are less represented in the integral. So that would mean in order to get the same average, in this case UB, you actually would need to increase the velocity in the center as to compensate for the fact that you have the geometry that is kind of changed a little bit. Which of course means now that the correct result is unfortunately exactly the one that got the least amount of votes, which is that the centerline velocity in a pipe is actually faster than in a channel to obtain the same bulk velocity, because the area of the center region is lower. So the correct result for this equation would be actually 1/2 of UCL. So in the pipe, it is, or in the channel, it is 2/3 of UCL. In the pipe, it is 1/2 of UCL. And again, the fact is, if you just kind of visually think of how this integral needs to be done, you will then realize that the center needs to be faster. And actually, this turns out, I mean, you can now think that this is a very trivial result, which of course it is. You can just do the integral and then you know, so there's no discussion about it. But of course, it tells you that there is actually quite a significant difference in the mean profile when you compare channels and pipes. Something that may not be kind of obvious. So this geometry, so that the confinement towards the center is actually something that's quite relevant, not only for calculating here the bulk velocity, but also later on when it's about stability and so on. There will be a lot of results that relate somehow to this confinement in the center. Okay, so now we have figured out this, and I think now I would like to stop with this first, or conclude this first chapter, which was about exact solutions in primitive variables. Do you have any questions or any comments for this topic? If not, then I think we should actually go to the next chapter or the next topic. So let me just conclude this. And the next topic would be the vorticity equations. We're still talking about viscous flows, and we're still talking about exact solutions to the Navier-Stokes equation. So in that sense, it's not a new topic, but it's now a new way of calculating exact solutions. And at times, it turns out that using the vorticity equations, as opposed to the Navier-Stokes equations in primitive variables, actually has some advantages. Not always, but sometimes. Let me just write that down in a sentence. So the Navier-Stokes equations in primitive variables and with primitive variables, I really mean just the pressure and the velocities directly. So these are not always the most suitable representation representation for all possible problems. So not always we want to do that directly in the primitive variables. There's actually a lot of physics you can also learn from that. So therefore, the idea is to now define a new set of governing equations which may be useful at times. So therefore, we consider, so now we consider the so-called, or we consider the equations based on the vorticity. Of course, that means first we need to define what the vorticity actually is, and then we can start to understand what we mean with it. So the vorticity first is a vector, which is based on nabla cross u. So essentially, it's the curl of the velocity u. So you go from one vector, the velocity vector, into the vorticity vector. So that's and by applying the curl operation. The curl operation, of course, is a derivative. So there's derivatives in all directions, which of course means that the equation certainly will look different. Now, why would you do that? Well, there's a few interesting things that are, which we will see most of them later on. There's, one way is to study the effect of boundary conditions, because there will be certainly changes to that. At times, it is better to use the vorticity equations, or at least components of the vorticity equation, to study the stability, the hydrodynamic stability problems. We will see later on we will use a so-called velocity vorticity formulation. And it also turns out that for numerical simulations, the vorticity formulation has some advantages that may be that can be used at times. Not only advantages, because you have then issues with the boundary conditions, which we also mentioned here, but some in certain circumstances is actually a good way. And the last point I would also like to mention, it allows us at times also to study the physics of the problem in a better way, because you can clearly identify aspects that relate to vorticity transport, which may at times be useful to understand certain effects of both stability and turbulence. But let's now try to actually derive those vorticity transport equations, because then many of these things that perhaps now just sound like taken out of thin air start to actually make sense. Let's just start with some vector identities. Which we can then use to derive the vorticity transport equation. Identities. So for instance, I'm just writing that down, but you can check yourself. So for instance, if you have u times nabla times u, which essentially corresponds to the nonlinear term of Navier-Stokes, this can actually be written using the vorticity as vorticity cross u plus nabla times u squared divided by 2. So this is a vector which can be written as the cross product between the vorticity and the velocity plus the gradient of the kinetic energy u squared divided by 2. It's quite an easy derivation, and I invite you to try that out. The forcing term of Navier-Stokes, if we assume now conservative forces, which we typically do if we think of, for instance, gravity, we can write this F as being minus the gradient of some potential psi, for instance. This is for conservative forces. This is something we're going to use. And then also for the viscous term, we can do some approx or some simplification. Namely, if you have the viscous term, nabla squared times u. This can be written in terms of the vorticity. Also, this is something that I invite you to just check. It would be the same as nu times nabla cross omega. So these here are a number of identities that we can use to simplify our Navier-Stokes equations. So, okay. Now, based on these guys, well, we can essentially write down the Navier-Stokes equations as they were, just essentially including those. Maybe I can do that a little bit in two steps. So we start with du dt plus u nabla u is minus the pressure gradient, so gradient of P divided by rho, plus nu times nabla squared u. So this is the Navier-Stokes equations as we know them. And we just introduce all these vector identities that we have just written here. So we go to using the above identities. What we will get is du dt. Now we replace this one with this term, for instance. So that means we have plus omega cross u. The kinetic energy we keep in our heads for a second, and we add it at the end. Then we replace this term with this. So we have a minus, so we put it on this side. So we get like this. Actually, this is not a minus here. This should be a plus. So we get a minus nu times nabla squared. What I'm writing now. I'm sorry. Forget this. I was making a mistake. So I'm actually not replacing it yet. I'm sorry. So this is minus nabla times nu times nabla squared u. And this is essentially just the gradient of the pressure, which we have here, P divided by rho. And then we have the force here. So we have here the term from the kinetic energy. So we have plus u squared divided by 2, and then we have a psi here. Okay, so this is the first step that we could rewrite the equations. Now, the interesting aspect here is that we can now identify that whatever is written here in this equation, in this bracket here, so we have the pressure plus the kinetic energy plus a potential. This is actually something that we know what it is. Well, this is nothing else than the Bernoulli equation, where we also have the sum of the pressure plus the static pressure plus the dynamic pressure plus some potential. And in the Bernoulli equation, we should just say that this is a constant. But these terms essentially correspond to Bernoulli. The next step in this derivation would now be to actually, if we call this to be equation number 1, the next step would be to calculate the curl of these equations. So we do nabla cross this equation number 1. And of course, that would mean that I would now take nabla cross of the first term of the time derivative. So we get d dt of, well, of omega. Then if I do that for the second term, where essentially I have the curl of omega cross u. If I calculate that, I will get. I'm not showing it here, but you can again do that at home. What you will get as a result, you will get u cross nabla times the vorticity minus minus omega dot nabla u. So this one was then the second term, and then when I do the multiplication with the curl for the viscous term, we get minus nu times nabla squared of the vorticity. And then on the left hand side, we will have, on the right hand side, we will have nabla cross nabla of whatever is in these brackets. Now, the interesting point is, if you have something nabla cross nabla of something, so the curl of a gradient of something, this is actually 0. So that means this whole equation needs to be 0. So that means all the parts that were originally contained or were part of this Bernoulli equation that we just identified, these guys actually disappear. In particular, what you can see here is that the pressure has disappeared, because the pressure, which was part in this Bernoulli part of the equation, has actually disappeared from the equations. So we have now written the Navier-Stokes equation without pressure. Okay, but now let's look a little bit more at the terms that actually remained in this. Well, I guess the easiest term to understand is essentially this one here, which is what we can directly identify as a vorticity diffusion term. It's just the second derivative of the vorticity and with the viscosity in front. So this is a vorticity diffusion term. These two terms in the beginning, these are just, or this can be also written as the capital omega dt, and this is nothing else as the material derivative of the vorticity. So we can essentially say that this would be the vorticity of a fluid particle as it kind of advects or through the domain. So it's just a material derivative of. Well, and then we have one more term here in the middle, and this is actually a term that is new. This is a new term, which we have not seen before. And of course, physically, it's kind of a term that relates to the pressure, or that used to be the pressure in the Navier-Stokes equation in primitive variables, which has now disappeared. But a new term has appeared, which is now the pressure. Okay, so this we can now say this is equation number 2. So the curl of equation number 1. And of course, we still have, and we have not used it, equation number 3, which would just be the fact that we look at an incompressible flow, meaning that the divergence of u is 0. So that would be the normal continuity equation. Okay, so now what we have what we derived is a bunch of equations. We have the first equation here, which is just Navier-Stokes, where we have put in one identity for the curl. Then we have equation number 2, where we took the curl of equation number 1. And we have equation number 3, which is the continuity equation. Now, how can we now use these equations to calculate solutions to the Navier-Stokes equations? Because as you realize, equation 1 and equation 2 are very much related. There's just one mathematical operation between them. You apply the curl to go from 1 to 2. So it's not new physics that goes in. So it's not independent equations. So therefore, it's still the question, how would now the procedure actually be? And for that, we can actually do the first observation. We can state. Wait. What happened now? Yeah. Okay. We can state now that equation number 3, equation number 2. So the new equation that we derived. This equation can be viewed as a compatibility condition. And this compatibility condition is exactly this vorticity transport equation, what it actually is. This can be assumed as a compatibility condition without actually having the pressure in it. So compatibility to what? Well, equations 2 and 3, so this compatibility condition plus the continuity equation together, they ensure that the vector field U that can be calculated is in such a way that a pressure can be calculated. Can be calculated. Using equation number 1. So the idea is that with equations 2 and 3, you can calculate a specific velocity field, which you can then use to calculate the pressure using equation number 1. So in that sense, that's what I mean with compatibility condition. Equation number 2 ensures that the vector field U, so the velocity field U, has a specific form that we can calculate the pressure using equation number 1. If it wouldn't fulfill equation number 2, it would not be, the U would not be a velocity field, a valid velocity field. But the important thing is we actually don't need to calculate the pressure if we don't want to. So that means now if we think of a kind of a procedure on how to actually use the vorticity transport equation number 2 to calculate velocity to calculate velocity, would be like this. The typical procedure would then be that the first step would be to use equations 2 and 3, so the continuity equation and the vorticity transport equation. You use these equations to calculate a velocity field U, and of course on also vorticity field omega. And then if you want, you can use equation number 1 to calculate a pressure field, or calculate the pressure P. But again, the important thing here is that the vorticity transport equation is not a new equation. It's just a reformulation of the Navier-Stokes equation where the pressure is not present. But of course, if you want the pressure, you need to calculate it afterwards. So that's the basic idea of how to handle these equations. And I said it now a few times, but equation number 2, that is exactly the vorticity transport equation where we have the material derivative of the vorticity, d omega dt, minus this new term, minus the vorticity diffusion equals 0. So it has kind of the typical components that you would expect for kind of a fluid equation. You have a material derivative, you have a viscous term, and then you have some other term that does some magic to it. In this case, it's this new term, which we'll discuss later on what it actually does. Let's do an example. Let's do a quick example here, where I can hopefully illustrate what I mean with all these, compatibility conditions and so on. Let's look at potential flow. So what is potential flow? I mean, if you think back to Professor Talamelli's presentations or lectures, well, potential flow is irrotational flow. It's irrotational. That means that actually the vorticity needs to be 0. Well, and at the same time, we know that we can write the velocity as a gradient of something, a gradient of phi, which in this case would be the potential. And we also know that the second derivative of this potential would then be 0. Okay, now what would that means? So how can we kind of use this to illustrate that the vorticity transport equation can be viewed as a compatibility condition? Well, the vorticity omega would now be defined as the curl of the velocity, and if we now do that with if we just put in the definition with the potential, so we have nabla cross nabla phi, and of course this becomes 0. So that means now that although we have now written it here in the beginning, but in principle this is a result of the fact that we could write it as a potential. But now in the context of the vorticity transport equation, we now realize that omega actually needs to be 0 given that particular velocity field. And now for us discussing the aspects here with compatibility condition, it means that using a velocity field which is defined as a gradient of a specific phi is actually fulfilling the compatibility condition. Compatibility condition number 2 is fulfilled. Of course, this is fulfilled here in a trivial way because omega is just 0, but still it means that equation 2 is fulfilled because all the omegas here, all the omegas are 0, so that means equation number 2 is actually fulfilled. And that means now that together with equation number 3, which is that the divergence condition is fulfilled, together with that condition, it actually means that the u velocity field that we have defined here is actually a solution to equation number 1, which was the Navier-Stokes equation number 1. Okay, so this was one example of showing you how we can actually use this idea of having the vorticity equation as a compatibility condition on the side. Okay. Now this was one example. The second example that we can just very briefly start, but we will probably not conclude it very much, but we can start and then we can get back more next time. The next example would be to look at the vorticity in plane Poisson flow. Also there, kind of in an effort to understand what is actually meant with the vorticity. So let's sketch briefly how the channel flow or the Poisson flow looks like. So we have again these two walls. We have our velocity field, which is this parabolic profile that we have introduced. This is u of y. We have, of course, our coordinate system, which has the origin here in the middle. So this would be y, and this would be the x direction. Well, actually, we can write it. Maybe we can do it like this. We can plot it on the side. It's maybe better. So we just introduced the coordinate system here. So we have x, we have y. And now because we talk about the vorticity, we actually need to do it in 3D. So that means that the z component would be for a right-handed system in such a way that it would actually look out of the plane. So it would come out. So x, y, and z coming out of the plane. Now, how does the vorticity of this velocity field look like? Well, it actually turns out there's only one vorticity component that is non-zero. And in this case, that would be omega z. So the vorticity component in the plane orthogonal to the paper. So omega z would now be something like minus du dy. That is the only component that is non-zero of the vorticity, because all the other terms would contain derivatives ddx and ddz, which are zero. So we have minus du dy, and now knowing how the velocity profile looks like in a channel, this actually becomes 2 times UCL times y divided by b. Again, maybe just for completeness, we said that this height would be 2b. Okay, so how does this vorticity now look like in the channel? Well, we can just draw what we have here. Well, let's just, it's linear here, so it will be something like this. So this here would be the vorticity. I'm indicating here with the arrows, you know, that we have positive and negative values for the vorticity. So this here, so the red bit here would be omega z of y. Okay, so what does this actually mean? Well, vorticity is the curl of the velocity, and the curl, of course, as the name says, kind of indicates some sort of rotation in the quantities. Now, if we have a positive omega and we just look at a positive rotation, that would mean that in the upper side, we would essentially have a rotation which would be like this. So the idea is that we have a right-handed system. So if the thumb is in the direction of the vorticity component, then the fingers indicate in what direction it would actually rotate. So in this case, because it's positive, so the thumb would look upwards. So we have a rotation counterclockwise. Whereas in the lower side, where the vorticity is negative, vorticity vector points down. So we'd have a clockwise kind of rotation of fluid elements. Now, why is this the case? Now, again, think physically. Let's assume we have two fluid particles in this shear flow, in this plane Poisson flow, just next to each other at slightly different y positions. Well, it means that the one, so if I'm indicating it here, so maybe one here and one here. A little bit later, it turns out that the one that was a little bit closer to the center was traveling a bit faster. So that means that later on, maybe this has traveled here and this has traveled here. So that means that this vertical line suddenly became a little bit tilted. And of course, it has become tilted exactly in the way as we have predicted with how this rotation would look like. So that means you can essentially identify the vorticity as a change of orientation of a fluid particle in the flow. So as a kind of a local rotation that the fluid particle would experience. So we can say that the vorticity acts as a change of orientation of a fluid particle or of fluid particles. Particles. So that corresponds essentially to a rotation that these particles do. And of course, that also means that in the center of the channel, so in this place here, the vorticity is actually 0. And of course, at those places, there is no rotation present for these particles. So nothing is happening there. So that means at the end, we can actually associate the vorticity being related to an angular velocity. And it turns out that is actually a factor of 2 times the angular velocity that you would have in a local position. So the value of the vorticity can be related to 2 times the angular velocity, rotation speed that you have as a certain position. So locally, the vorticity can be related to a rotation of fluid elements, which you can quite easily see in the channel with this example that I just made. Okay, so I guess with this we can also close for today. What I wanted to show you now with this first introduction to the vorticity equation is kind of the idea that this is a compatibility condition to provide correct velocity fields, and that the vorticity can be viewed as a kind of a local rotation inside the dome. Next week we have another lecture on Tuesday from 3 to 6, and then we have another one on Thursday. However, the one on Thursday I would actually like to cancel because we have actually 11 times and only 10 lectures. So the one on Thursday I would like to cancel for next week. So next week we only have one lecture on Tuesday from 3 to 6. Okay, so with this I would like to close for today. Thank you very much for your attention, and have a nice weekend, and see you again on Tuesday next week. Thank you.